Hello, in this video we are going to have a look at the essential Year 12 topic of spectra. Okay, now spectra are a bit of a phenomenon that we see. So think about when you put light through a prism. As the light travels through the prism, the red light bends less than the blue light or the purple light. Refracts less than the purple light, and what we see is a spectrum, and you've seen this before. It's a rainbow. Now sometimes if this light then goes through a cloud of gas, when you look at the spectrum, instead of seeing the rainbow, what you see instead is the rainbow with black lines in specific places along it. And this is called an absorption spectra, and I can't, colour in the rainbow. Absorption. Sorry, my handwriting's terrible. I can hear people talking and it's confusing me. Okay, so that's called an absorption spectrum. Or sometimes what you might do is you might, for example, burn an element. So burn an element in a Bunsen burner. And if you burn an element and then you look at it through a spectroscope, this also needs to be looked at through a spectroscope, by the way. If you look at it through a spectroscope, what you will see is that different elements burn with different colours. It's called flame test. You might remember it back from chemistry. And those different colours will be, if you look at it through a spectrograph or a spectrometer, you will notice that those colours are in the order of the rainbow. I'm on limited numbers of colours here. And you'll get a black background with just these colours of light poking out. This is called an emission spectra. So this is all black, apart from these bits of light. And this one here, this is a rainbow underneath it, but I can't colour in a rainbow with my hand quickly. And these both need to be observed through a spectrometer or a spectroscope. Now, if these are the same element, then these gaps and these lines will match up. And this is actually really useful because it means that we can use emission spectra and absorption spectra to work out what elements are in a gas, if it's in space, for example, far away, or if we've got an unknown substance, if we burn it and then look at it through look at the emission spectra, we might be able to work out what the stuff is made of, what elements are in there. Now, what we need to know is why this happens. Why do we get these specific lines? And they happen, these lines are at specific wavelengths and frequencies for each element. And each element will have a different kind of pattern. So a different element might, instead of having this, have something that looks like this instead. So each element will have different patterns. Now this is all because, it's very, very important, electrons exist in discrete energy levels. And the word discrete there is important. So electrons exist in discrete energy levels. If you think about an atom, you've got the nucleus, which has got protons and neutrons in it. And then around that, you've got your electron shells. And the electrons can only exist in these shells. Okay. Now this is a helium atom because it's got 2 protons and 2 neutrons. And a helium atom will have 2 electrons, and those 2 electrons will live in the first shell. But if something comes along, for example, another electron, or potentially some light, a photon of light, something comes along and hits that electron, it can cause the electron to be excited and jump up to a higher energy level. This is called excitation. Now, if it's light that is causing this, there's a very specific time when it happens. If it's an electron that's knocking into it, it's the Ke of the electron that's causing this, and we'll talk about that in a moment. for both of those. But that will leave behind a gap in this lower energy level where that electron used to be. Now, eventually, this electron that's been excited is going to fall back down. Okay, we can say it relaxes because just like people, electrons are lazy. For example, imagine that you're on the bus and there's no seats, you're going to stand up. As soon as there's a seat, you'll probably go and sit down. As soon as there's a gap, you want to go and be in that lower energy state. So electrons can be excited or they can relax and fall back into gaps that are below them. Now, these discrete energy levels, we often draw them, instead of drawing them as you've just seen there. You can really see through that piece of paper, can't you? Let's switch on to this one. It's my scrap paper. Okay, we often draw them, instead of in a circle, we draw them like this. And this is the ground state. We often call it n equals 1. And then we have the first excited state, n equals 2, the second excited state, n equals 3 even, and the fourth excited state, n equals 4. And these different states will have different energies. Now, the energies are actually negative because they're potential energies, and we usually write them in terms of electron volts or mega electron volts. So I'm going to just put some numbers in. I'm going to say that this is minus 15 electron volts, and this is minus 12 electron volts, and this is minus 8 electron volts, and then minus 2 electron volts. And then you often find there's quite a lot at the top. And eventually you get to 0 electron volts. And essentially there are an infinite number of these energy levels, but we only really care about the first couple. Now, if an electron is in the ground state, and a photon comes along, a photon, remember, has energy E equals hf. So the energy of the photon depends on the frequency of the photon. So a purple photon, a violet photon, would have a higher energy than a red photon. But red is unfortunately going to be a pink pen for today because my red pen's gone missing. So the pink one, the red one, has got a lower energy because it's got a lower frequency, a longer wavelength, and the purple one's going to have a higher energy. Now, if the energy of the photon is equal to the energy difference between two levels, the electron will jump up to that level. Okay, so let's say, for example, the pink or red photon has got 3 electron volts of energy. This electron, if it absorbed that photon, will jump up to this energy level here, because minus 15 plus 3 is 12. The gap there is 3 electron volts, so it can jump up. If though, maybe the purple photon had 7 electron volts of energy, then this electron, instead of jumping up to the first excited state, it will jump up to the second excited state, because minus 15 plus 7 is minus 8. However, let's say we also had a blue photon coming along, and the blue photon will have a middle energy, and let's say that's 5 electron volts. If this electron absorbed the blue photon, nothing would happen, because the photon energy has to be equal to the difference between the energy levels. It can't, even though it's bigger than the first one, I know that it's more than 3 electron volts, it can't just get to the first level and then just keep the rest of the energy spare. It uses all the energy or uses none of it. And this is the start of something called quantum mechanics, and this idea of discrete energy levels and having to use exact amounts of energy. Now, when an electron jumps up, what happens is the photon is absorbed. So some light is absorbed. And this is what's going on in an absorption spectra. So we've got all the light, And then when the light goes through the gas, that's where we get photons hitting the electrons in the gas and being absorbed by the gas. And so when the light comes through the gas, these colours here that are missing, they correspond to these energy levels here, the photons that have been absorbed, which corresponds to the difference between the energy levels for this particular electron. So the photon is absorbed, and this causes an absorption spectrum. Now, an emission spectrum is very, very similar, okay? For an emission spectrum, though, I might start a new page for this, I think I will. So let's go for the same levels as before. I'm not going to draw them all. So minus 2 eV, minus 8 eV, minus 12 eV, minus 15 eV. What often happens in an emission spectrum is that to start with, the electron gets knocked by another electron with Ke. And this electron will it'll knock that, and then it'll carry on with less Ke than it had before. Put that bit there. Okay? But it causes this electron to jump up to an energy level. Maybe this one. Okay? Now, when this electron jumps up, there's a gap left where it was. And eventually, the electron is going to fall back down again to where that gap was. Now, when it does that, it can't just get rid of the energy that it gained. It has to somehow get rid of that. And it gets rid of it as a photon. And that photon has energy E equals hf, but it also has energy equal to the energy difference or energy gap between the levels. Now, if instead, let's say that the electron had been jumped up to this one instead, to this energy level, when it fell down, it would release a photon with less energy and as E equals hf, a lower frequency. So a more red photon. And there's a reason I've kept these the same. So to get from 15 to 12 electron volts, I'm absorbing my red photon. And when I jump back down from 12 to 15, I'm going to emit the same colour, the same red. And to get from 15 to 8, I'm absorbing a purple photon. And to get from 8 to 15, I need to emit a photon, which is going to have the same frequency, the same energy. And this is how I get the emission spectra, because the electrons are being knocked up by other electrons, but they're being excited by other electrons or by heat, for example, if it's in a flame test. And as they fall down, only certain falls are allowed. They can only fall from here to here, or from here to here, or from here to here, or from here to here. So we only get certain energy drops that are allowed. And it's these differences in energy levels. My writing is really bad today, I'm sorry. And different falls that are allowed that mean that each element has its own specific spectra. So that's a very quick explanation, but I've also got some questions to do about this. So I'm going to do in a new video some questions, exam questions, and spectra exam questions are famous for having basically the same mark scheme over and over again. So it's really worth having a look at that. Hopefully that was helpful.